Hi, today I would like to show you some of our results on the leaf scale heat exchange in semi-arid forests. First off, in semi-arid forests such as our research site in Yatir, the high incoming radiation and low albedo should theoretically lead to a large increase in forest surface temperatures. However, a large sensible heat flux has led to cooling of the canopy via a convector effect, and this was first observed by Rothenberg and Yakir in 2010. Additionally, low leaf-to-air temperature differences allow leaves to survive the harsh conditions of those dry environments. This means that heat has to be efficiently exchanged with the surrounding air. Our aim, therefore, was to examine the non-evaporative cooling mechanisms that form at the leaf scale and provide an efficient leaf thermal management. For this purpose, we developed a system based on infrared imagery to accurately measure leaf temperature, since thermocouple-based systems were difficult to use and easily lost physical contact with the leaves. The system consisted of a PAR sensor, here in green, a high emissivity reference plate in red, a low emissivity reference plate in yellow, and a thin air temperature thermocouple in blue. I will come back to the details of this system. Now, we deployed the system in the field in the peak of summer drought in both a plot that was not limited in evaporation because we irrigated the trees, and a controlled plot in which the trees were completely exposed to summer drought. First, we did a calibration for the systematic infrared camera offset using the high emissivity reference plate that I've mentioned before. Then, using the low emissivity reference plate, we measured the background thermal radiation. And finally, the simplified equation for infrared thermography published by Incropera et al. In 2006 could be resolved for leaf temperature, here. The graph on the left shows the correction effect of using the background thermal radiation in conditions that we encounter typically in our field site, which can lead to corrections of up to 1.5 degrees Celsius, as can be seen here. As for results, under this high radiation load, we observed that the leaf-to-air temperature difference, delta T, reached only about 3 to 4 degrees Celsius in both the irrigated and the drought-exposed control trees, without any significant differences, as can be seen here. This is surprising considering the transpiration that is approximately 10 times higher in the irrigated trees, as seen here, and it shows that heat dissipation through latent heat does not significantly cool the leaves. In conclusion, our system was able to accurately measure leaf temperature throughout the seasons and the difficult harsh conditions of our site. We were able to show that there is an effective leaf-to-air heat transfer that prevents overheating of leaves in semi-arid forests. This, of course, is crucial for plant survival in this climate zone. Finally, the low delta T is the basis of the large sensible heat flux observed above those forests. But because delta T remains low, as can be seen here in the sensible heat equation, the aerodynamic resistance RH here plays an important role and needs to equally be low for a large sensible heat flux, and we aim to discuss this in upcoming research. With that, I've reached the end of my presentation. Thank you very much.